Okay, recording done. All right. So we're gonna go into electromagnet. That'll be already. Okay, the previous lessons we already covered electric already. So we're gonna go into electromagnet today. In case you guys can't hear me or my connection is not very good, do send me a message so that I will be aware of it. Okay. Okay, electromagnetism, previously in terms of syllabus wise, you all actually learned it in Form 3 again. But I know you're already in Form 5 right now, so there are some syllabus that you all don't really remember in Form 3. So because of that, we will do a little bit flashback, right, on electromagnetism. Okay. So for electromagnetism, first thing what we need to understand is the word of electromagnet. Now, in electromagnet, okay, right, right, in terms of electromagnet, it comes from two words. First is electricity, and the other one is magnet. Okay, so in this chapter, what we will be learning is two parts. Okay, we will learn about using electric, all right, electric to generate magnetic field. And the second part is actually using magnetic field to induce electricity. And then the fourth part we'll learn, the third part we'll learn about transformer. And finally, um, the national grid system, whereby how we transfer the electricity throughout the whole entire country. So these are a few things that we are going to cover. All right. So let's go to the first part. What is an electromagnet? Okay. In terms of textbook wise electromagnetism, they went directly into a current carrying conductor, all right, whereby they use the Fleming left hand rule and Fleming right hand rule. So I'm gonna do a little bit recap on what is electromagnet first. Okay, so electromagnet. Okay, the definition for electromagnet is, let's see, okay, they don't have the definition of electromagnet over here. So electromagnet is a temporary magnet. All right. We have normally when we talk about permanent magnets, we talk about there is an existence of north pole and south pole directly already. All right. If we have a normal magnet, we have the north pole and the south pole, and we know that the magnetic field line will come out from the north pole and then it will enter the south pole. Right, so all these are magnetic field lines. So magnetic field line symbol in physics is actually capital B, all right, whereby electric field lines is using capital E. The difference that they always say is that if you were to break a magnet, if you were to break a permanent magnet into half, it will automatically generate a north and south, even though it has already been broken. Okay, so it will always exist in pairs. Okay, magnets will always exist in pairs in terms of north pole and south pole. Okay, so electromagnet, right? Electromagnet is actually when a conductor, there's a current carrying. I just noticed this here. When a current flows through a coil or a current carrying conductor, it will produce magnetic field. So that is a electromagnet. Okay, so it can be made by sending electric current through a coil. So previously, um when we talk about electricity in the previous chapter, okay, when we talk about electricity, we talk about when there is potential difference. All right, when there is potential difference, then there will be charge flowing. All right, when there's charge flowing, then we will have current flowing. Okay, so over here, right, when there's current flowing, there will be electric field. So right now, an additional in this chapter is whereby when there's current flowing, it will actually produce a temporary magnetic field. Okay, it will produce a temporary magnetic field. So you don't need a magnet bar to create a magnetic field, you just need a current carrying conductor, which means that in the wire that is current flowing, then it can actually create a temporary magnetic field. So that's what electromagnet is talking about. So electromagnet over here, okay, the soft iron core becomes temporarily magnetized when the current is switched on. Okay, this one I have to explain a little bit further because I've just finished marking gamma's section B and section C, and there's many people written soft iron core conductor. Okay, now the soft iron core that we are talking about is not the wire. You have to clarify regarding this. Okay, when there's a power supply positive and negative terminal, all right, current will flow from the positive through the circuit towards the negative. That is the conductor. The soft iron core that we're talking about is this one, you know. All right, we are talking about the soft iron core is this particular part. Okay, because regarding the homopolar question, all right, it's not the wire that is supposed to be soft iron core. All right, it's not the wire, but it's this metal over here. All right, this metal here is soft iron core metal in the middle of the wires. Okay, it's a different question that the trial question was asking for. Okay, so the soft iron core, it actually helps to magnetize and demagnetize even better to create a stronger magnetic field. All right, over here we use a soft iron core when there is no magnet. The current carrying conductor, which is the wire, is the one that magnetizes. When current flows through the wire, it becomes magnetized. It will create a temporary magnet. So if we want that temporary magnet to be even stronger, we insert a soft iron core in the middle of the coil. All right, we insert this soft iron core in the middle of the coil to strengthen the magnetic field lines that is being created. All right, so I hope this clarify the information for all of you. Okay, so but one thing, electromagnet, the first part we're talking about is electricity inducing magnetic field. So when there is no current flowing in the circuit, then it will lose its magnetism. The whole entire magnetism will actually be lost. All right, the key for electricity to to create a temporary magnetic field is the current must flow. So when the switch is off, the current is not moving, then there is no magnetism over there already. All right, the soft iron core, um main function for the soft iron core is actually to enhance the magnetic field lines. Okay, it's not to enhance the current flowing and everything. Okay, again, if you guys have any question, you can just message inside the chat box. Wait, let me see. Okay, all right, because I'm using a tablet, I don't have a dual screen at my hometown right now, so I still can see the message if you guys have anything inside the chat box. Okay, so what is magnetic field patterns? Okay, magnetic field patterns can be represented by field lines that shows the shape of the field. Magnetic field lines are close together to represent a strong field, and the field direction is defined as direction indicated by the compass needle placed in the magnetic field. So, all right, how does magnetic field lines is almost similar to the electric field lines? Okay, right? It's almost similar to electric field lines. It's just that magnetic field lines will come out from the north pole and it will enter the south pole. So if in terms of what we're going to look at is the right hand grip rule, okay, this is all refreshing your memory from Form 3 here. Right hand grip rule, we are using our right hand over here. Let me see. Let me move my. Okay, so I'm not very quite sure if you guys can see my hand properly or not. Okay, so right hand grip rule, we in this whole entire chapter, we know you know that we need to use three hand rules. We have the right hand grip rule, that's the first one. Okay, now for me, whenever I teach my student regarding right hand grip rule, I will first talk about this hand sign. This hand sign is obviously we all know it's the like hand sign in the Facebook, correct? So whenever someone click like on your Facebook, you will actually feel good. So the word feeling good when you see the like hand sign. All right. So for me, right hand grip rule, the good sign will actually represents the magnetic field direction. It's for us to determine the magnetic field direction. So we have the thumb. Generally, the thumb is actually used to represent the direction of current, whereby the fingers will represent the direction of the magnetic field. Okay, so in this case, right, there's certain situation where we will switch. I will teach you one by one on how to identify it. Okay, so alamak. Okay, right. So in case of a straight current carrying conductor, okay, so I'm gonna use I sorry if you hear that motor sound, that's the annoying sound of the people outside. Nadira. Okay, so over here, all right, we have a current carrying conductor. The first thing that you need to do, please make sure that when you are entering in the class together right now, make sure you have a paper and pen with you. All right, don't just stare at the handphone or stare at the screen. Okay, make sure you have your paper and pen with you because learning the hand rules in this chapter, you need to write it down also. So, how do we identify? Number one, determine the positive and negative of the battery first. All right, the positive and negative terminal of the battery. Then after that, what you have to do is number two, all right, draw the arrow for the direction of current throughout the whole circuit. Okay, then after that, what we need to do is at the point where we're gonna draw, we are gonna determine the magnetic field. All right, draw at least three circles that is not touching each other. All right, that's not touching each other. Then after that, use the right hand grip rule to determine the direction of magnetic field. Okay, so I'm gonna start right now. So I hope you have already drawn this piece of paper or you have already printed out and you're ready for this. Okay, so first thing first, number one, determine the direction, the positive and negative terminal of the battery. So this is the battery over here. So the longer one represents positive terminal, the shorter one represents negative terminal, and the current will flow out from the positive terminal. This is our current flowing throughout the whole entire circuit. All right, so we're going to draw on this piece of paper. So make sure you draw the arrow pointing downwards, coming out here towards the negative terminal. All right, so we have determined the direction of the positive and negative, and we have already drawn the direction of the current flowing. Okay, so draw at least three circles that is not touching each other. So we're going to draw three circles right now at this piece of paper. So one, try to draw as best circle as you can now, okay? Since I'm using freehand, this is the best that I can do. Try not to touch. The lines should not touch each other. All right. So now how are we going to determine? Okay, I don't have paper here. All right. So how we're going to determine is, let's see. Let's see one thing. Ignore that. Okay. All right. So I have to, there's nothing behind me anyway. Okay. So what we're going to do is right now the paper is, imagine this is the paper. All right. So I'm going to use the tip of my drawing pen pointing downwards to represent the direction of the current. Okay. All right. So what I'm going to do is using my right hand rule. All right. I'm going to point my thumb downwards. Okay. Why? Because on the paper itself, the current is actually pointing downwards. Okay. So it would be a good idea for you to put your hand directly on the paper. All right. To point it downwards like this and then grip the pen or whatever is in front of you. Okay. So what happens here is when I'm doing this, I'm looking at the question in front of me. Okay. So when I'm looking at the question in front of me, let's see if I can. I know you guys are having difficulty of me identifying this. Uh, okay, I'm gonna try one thing. All right. Can you all see I have another tablet that it's on right now? There's another screen on right now. Can you all try to switch to that view? Okay. If you can see at the other part of my tablet, there's another video on right now. So you can see my hand, just my hand and the screen in front. So what I do is normally I have the paper in front of me, okay, and then I will point my thumb downwards in front of the question paper, and then on the left side of the question paper my fingers are actually pointing inwards, and then on the right side my fingers will come out. Okay, so that is actually how I determine the my direction. So in the case of this situation, hopefully you guys can see, I will try to get paper and pen the next round. So when I actually do this, all right, in front, on the left side, you can see that the fingers are actually going in. Okay, so when it's going in, then on the screen or on your paper, you draw the arrow going in. And then over on the other side, my fingers is actually curling out. All right, on the right side, my fingers are curling out. So on the on the circle also, it should curl outwards. All right, so that is how we determine the direction of magnetic field for a straight conductor. Okay, in case like what the question, the note said just now, if I have a compass here, all right, I place a compass at this part. We know that compass generally should face towards North Pole. All right, the arrow of the compass should always point towards the North Pole. But when we place a compass near a current carrying conductor, all right, when we place the compass near a current carrying conductor, the compass will not point towards the North Pole anymore. It will point towards the direction of the magnetic field created by the current carrying conductor. So in this situation, this compass will point same direction as this arrow. All right, over here, because the arrow should follow same direction, ma. So the compass behind here will point towards the right. At this side, the arrow will point towards, compass will point outwards, and then at this position, the compass will actually point towards the left hand side. All right, so that is how we determine the direction of magnetic field using a compass physically. Okay, up to here, is there any question? Are you guys okay? You can just directly yes no inside. Okay, good. Now, the next one, would be, okay, the notes over here, they are actually using this direction. Okay, view from the top. All right, if there is a magnetic, we draw the magnetic field line, this is going downwards. Just now we know that it's actually going clockwise already. All right. So that's why you will see a clockwise. Now, how did this arrow and dot comes out from? This arrow and dot actually comes from the archery arrow. The archery arrow, if you were to look from the front, all right, you would see a dot. But if you look at the archery arrow from the back, you will see a cross. Okay? So that's why when you see a cross, this means that the current is entering the paper going downwards, because this picture is the view from the top. All right, the current is going into the paper, which means we are looking at this paper from the top view. So in this direction, on the right hand side, the last picture, okay, the current is actually moving upwards. So you see a dot because the arrow is actually pointing upwards. So you see the dot of the arrow. All right, when you determine the direction of the magnetic field, your thumb is actually pointing upwards. So from the top view, if you were to put your hands on top of your table or on top of your paper, from the top view, you will actually see that it is actually going anti-clockwise. All right, so that is how we see this direction, whether is it going clockwise or is it going anti-clockwise. Okay, but please remember one thing. Make sure that when you draw this arrow, it has to go all same direction. I've seen students drawing like this. On the left it goes up, on the right it goes up again. All right, so this one you'll get it wrong. Okay, but I don't think so they'll ask you to draw lah. I'm just explaining just in case right now, because these are prior knowledge. They can ask prior knowledge questions. All right, next is actually for a coil. A coil is just taking a piece of wire and they just bend that wire only. All right, so in order to analyze a coil, okay, let me get this here. Same thing as just now. All right, same thing as this indication. Okay, so what we have here right now is determine the positive and negative terminal of the battery. So positive is the longer line, negative is the shorter one. So current flows from positive coming out here. So this part is coming out. All right, so this part is coming out, going upwards, coming back in towards the negative terminal. So that's the current. The color doesn't really represent anything much, so don't worry about that. Okay, so now I've determined the positive, negative. I've drawn the direction of the current. Now draw 3 circles. Now for a coil, how do we draw? Number 1, coil have to slightly different. You draw a straight line in the middle. All right, straight line in the middle, and then you draw 2 circles over here. Make sure you don't touch them. Okay, you want to draw 3 also can, no problem. If I'm going too fast, make sure you let me know. And then here in the middle, just do a curve like this. Okay? Alright. Are you guys okay? I'm stopping here. I'm just taking a break over here. Scared you're tak. Can I proceed already? Okay, I think should be okay, yeah? Alright, good. Thank you. Now, so we determine using the right hand grip rule also, but we determine we have to analyze one by one. So we analyze on the left hand side first. So on the left hand side, the current is actually coming out. Right? So coming out again using your thumb, pointing upwards. All right. As you can see, when I am current coming up, pointing upwards, you can see my screen directly here. Over on the left hand side, it is actually coming out. All right, so here, this is coming out. and just follow, let the arrow goes in a complete circle like this. Okay, so that is right hand pointing upwards, your thumb pointing upwards. The magnetic field will actually turn anti-clockwise, and then when it's pointing downwards, all right, when the thumb is pointing downwards, our fingers are actually going clockwise direction. All right, again, the clockwise direction is the view from the top. So I have a habit of drawing the circles all the way. All right. So now, how do we determine the lines in the middle? The lines in the middle are actually very easy. You look at the two lines here. Both is actually pointing inwards. So the three lines in the middle will follow the same direction, no? All right. So this one will come out. Here will enter. All right. So this is how we determine the direction for the coil. Okay. Up to here, are you guys all right? All right. Good. Okay, so last we're gonna go and look at solenoid. So you see, this is the same picture that I've drawn just now. All right, the last picture is actually the solenoid part. Okay, so for solenoid, you'll be thinking, am I going to analyze one by one every single point that it comes out? No, really don't need to. All you have to do here is number one, first thing, determine positive, negative of the battery. All right, remember the longer one's positive, the shorter one's negative. Then the current flows out from positive, and then here it goes like this, upwards. And then current comes back down. Okay, now, so how am I going to draw the magnetic field lines? Number one, draw a straight line in the middle. I'm going to use a ruler. Okay, I'm going to draw a straight line in the middle, and I'm going to draw a line over here. All right, then what I'm going to do is I'm going to draw a circle around here. Because I have to draw such a big picture, please excuse my line not touching. It's supposed to touch. Okay. So here, curve. And then in the middle here, okay. So how am I going to determine the direction right now? So I'm not going to go and analyze one by one every single uh current coming out. So what I do is my right hand grip rule, I'm going to switch the task. I'm going to switch the position whereby the thumb previously was to represent the direction of current, because there's only one current coming out. So right now I'm going to represent my current using my fingers. Okay, so over here what you have to do is, since you guys are using the laptop or your handphone, right, take your right hand, put it in front of the screen, let the fingers follow the direction of the current. So if you're gonna put your hand in front of the on the screen, right, let's just say this is the screen right now, you follow the fingers going upwards. All right, when you follow the fingers going upwards, you can determine that the direction of the current flow. So when I put my fingers in front of my screen and let my fingers follow the direction of my current flow, my thumb is actually pointing towards the left hand side. All right, so when it points towards the left hand side, it means that my magnetic field is going this way, coming outwards this way. This is north because magnetic field comes out from north, and obviously everything inside there will actually move towards the north. I repeat, everything inside is moving towards the north. All right, so here would be the south pole. Now, if you notice, I did not draw the arrow for the outer one. I just mentioned that everything inside will move towards the north direction. So the north is pointing towards the left. So every single line inside that solenoid is moving towards the left. So for the circle that is on top and below, you follow the direction of the arrow lor. So the arrow points here, arrow goes up towards the right, and then it enters back. Shouldn't north and wait Vinaya. Alright, so this one goes this direction and pointing towards south. Vinaya, what do you mean by shouldn't north and south pole be interchanged?
Because um the lines in the South Pole right now are going out of it. Shouldn't the South Pole it should go inside?
South pole here is going in up. This part, this one is going in, right? For my view.
Like it should be going into the South Pole, not going out from it.
My south pole is on the right hand side wall. So it's entering south pole. North pole comes out, south pole goes in. So in the middle, it should go this direction.
Oh, it's making like a circle outside of the.
Yes. So
Okay.
technically to say if there's a circle, right, it should go like this. Like
Okay, it's
this.
understood. Yeah.
Okay. Alright. Okay. So the rest you all understand that? Should be okay, right? Okay, not okay. I'm seeing the chat box. No response. Okay. So you do have to remember that the the thumb, all right, the magnetic field will always exit from north pole entering south pole like this. All right, it will exit from the north pole entering the south pole. Okay, so that is the basic of electromagnet. So how are we going to increase the strength of the electromagnet? Number one, you increase the current flow. All right. To increase the strength of the electromagnet, you have to increase the current flow in the solenoid. So please do take note one thing. When we talk about electromagnet, we generally will focus on current flow. All right. Because they in this chapter you would notice that there is very few formulas except for transformer. All right. The main reason because to calculate the magnetic field, all right, magnetic field, they have their own formula. And this formula they did not teach in secondary school level. But in the formula itself, it actually shows the number of turns. All right, in the formula itself, the magnetic field has something to do with the number of turns. It has something to do with the current. It has something to do with the distance, all right, the distance between the turns. So that's the reason why they didn't really teach that, because they just want you guys to understand the concept of electromagnet for secondary school level. Okay, so over here it is best not to mention regarding uh stronger, how to say, potential difference. You should mention the word more current provided or higher current provided. All right, because in terms of concept wise, electromagnet is determined by the current. But obviously, yes, it's true that um we want to have higher current. It also depends on whether the potential difference is higher or lower. Okay, but you do need to understand when we talk about potential difference, we need to talk about the resistance as well. So for electromagnet, we focus on the current flow. All right, the higher the current flow, the stronger the electromagnets. Then for number of turns, also the same. The higher the number of turns, the stronger the electromagnet. Then the distance between the turns means that the distance is supposed to be closer. All right, closer distance between the turns, which means, how does it means by closer distance? Which means that, let's just say for example, if you can see my screen right now, all right, if I coil the solenoid like this, you can see that it's actually quite far away from each other. But if we were to get it close next to each other like this, all right, we coil the wire closely packed like this will actually increase the strength of the electromagnet. And the soft iron core is represented by this particular drawing pen. All right. The soft iron core is this drawing pen. It has nothing to do with this wire. Okay. So the usage of the soft iron core is, even without the soft iron core, there's magnetic field created already. But in order to strengthen the magnetic field, the electromagnet that is being produced, we put a soft iron in the middle over there. Okay. So the soft iron core has nothing to do with a wire, conducting wire. Okay. So, all right. Up to here, I hope that you guys are okay. You don't really need to learn regarding all this in terms of SPM syllabus voice. Okay. So that was a quick flashback on what electromagnet is all about. Give me 2 minutes to rest my voice first. So the for the rest of you, maybe 2 minutes for you guys to take a break. Because I'm in my hometown right now, and the fact that I have people to help me entertain my little girls, I can actually extend the time a little bit. So you do let me know if you guys can't just need a break or anything. You just let me know lah, ha. And somehow because of a holiday, it's the holiday timing, so I don't have to rush my girls to go to sleep so early. But connection wise, can I know is the connection wise okay for your from your side? Can you all see the videos? Is my voice lagging or anything? Hello, am I lagging? Ke semua dah hilang?
You're not lagging, Chef.
Okay, thank you, Vinaya. All right. Okay, so enough break for me. Okay, so this is the part whereby the actual syllabus in the textbook is written now. Okay, so in the textbook we were talking about the force on the current carrying conductor in a magnetic field. So what it's trying to say is that if I have a magnetic field like this, okay, so let's see. Okay, so if I have a north pole, okay, I have a north pole here, and obviously the south pole is at the top. It's just that we don't really focus on that south pole at a single bar over there. All right, and then I have another south pole at the bottom. Okay, so naturally this is a permanent magnet. All right, so the magnetic field lines will actually move from north towards south. You can see that it's almost similar with the electric field lines. Okay, whereby it bends a little bit in the side, but in the middle, when it's in the middle here, it's supposed to be a straight line. okay, parallel downwards. So what happens here is if I were to take a wire, okay, if I were to take a current carrying conductor, all right, I take a current carrying conductor like this, and I bring this current carrying conductor in front of the wire, all right, in front of the magnetic field. What will happen to this magnetic field? And there's current flowing inside that conductor. Keyword, there must be current flowing in the conductor. Okay, so there will be a force that is going to be created, and this force is what we talk about is using the Fleming left hand rule. All right, so I'm sure some of you have already already learned it over the trials. Again, I'm sorry for not being able to cover it properly before your trials, but I'm covering it right now. So what I want to clarify with you guys is that the usage of Fleming left hand rule and Fleming right hand rule. Okay, the usage of Fleming left hand rule is actually when there is power supply, right? Or there is charge flowing in the circuit, meaning means there is current flow through the conductor. Right? So Fleming left hand rule, we use it when there is power supply or there's charge flowing. Even if there's a single electron moving, right? A single electron is moving, that one also considered as using Fleming left hand rule. All right. So when there's a current flowing through the conductor, we use Fleming left hand rule. Fleming right hand rule is whereby there is no power supply. All right, there's no power supply in the circuit. Okay, there is no charge flowing, there is no current flowing in the circuit. Okay, so we use Fleming right hand rule. So what is in the circuit when in terms of Fleming right hand rule? What is in the circuit? There will be got resistor, right? There is a possible light bulb over there. There's a possible electrical appliances over there. Or sometimes they love to use the word load. All right, a load means electrical appliances. Okay, so over here, all right, this is how we determine whether to use Fleming left hand or using right hand. So left hand is for when there's power supply, right hand when there's no power supply. Okay, now, so over here, what happens is, okay, we have magnetdoor magnets. Okay, in terms of magnets, magnetdoor magnets is a normal magnet. A stronger magnet is actually called a neodymium magnet. Later, I'll show you guys. Okay, so then we have a low voltage direct current power supply over here. Low voltage, normally the range of the value is from 0 to 12 volts. All right, this is low voltage power supply. EHT. EHT stands for extremely high tension power supply. And this power supply normally is over a few kilovolts one. All right, it's more than a few kilovolts. It will go from 10,000, sorry, kilovolt, correct lah. 10,000 to 20,000, 30,000, 40,000, 50,000, and 60,000 kilovolts. So extremely high tension power supply is very, very high. And normally we won't let students to carry out the experiments for this lah. Okay. So in this case, what are we trying to find out is we are going to try to find out in let's me show this very clearly. That's the reason why I magnified it. So we have the magnetdoor magnets at the top and the below, and then it's connected to a power supply. All right. So when there's a power supply, what happens is, where is my pen? When there's a power supply, this one is normally negative, the black is normally positive. So the current will flow from the positive All right, current will flow from the positive,
Oh,
all right, through the copper rod. Copper rod is fixed one, you know. The copper rod will not move. All right, through the copper rod, passing through this copper wire, all right, and then going back to the negative terminal of the battery again. So the copper rod will not move. The one that will move is actually this copper wire will move because this copper wire is not fixed. The copper rod is fixed to the terminal. Look at this. It's fixed to the terminal, so the copper rod cannot move on, you know. So what happens is the question will normally ask what happens to this copper wire. So we have to use the Fleming left hand rule to determine the direction. Okay, so what happens to a current carrying conductor in a magnetic field? So, when a current carrying conductor in an electric field through another magnetic field, a magnetic force is exerted on the wire. So, how does this happen? Combination of magnetic field due to the current in the conductor. All right, this current in the conductor will create a temporary magnet. All right, and the external magnetic field is the permanent magnet. All right, the permanent magnet, when there's a combination from the temporary magnet and the permanent magnet, it will produce a resultant magnetic field, and this is what is known as the catapult effect. All right, so this resultant magnetic field produce a magnetic force which later acts as the current acts on the current carrying conductor. So how do we determine? We use the Fleming left hand rule. So the thumb will point to the direction of force, and force symbol is capital F. Magnetic field direction is actually from the south pole, because south pole entering ma, and coming out from the north pole. So our pointing finger will point towards north pole, and the magnetic field direction, magnetic field symbol is capital B. Yeah? Current direction, current symbol is capital I. Current direction, normally current flows from positive to negative. So our middle finger is actually from the positive towards the negative direction. All right. So how we determine, again, please look at the screen of me looking on the screen, my thumb. So I will determine it using FBI. All right, I determine it using FBI, whereby F represents the force pointing towards the direction of the force, B represents magnetic field pointing from that means from the inwards, this is actually south, coming out is north, and then my current, my middle finger will point towards the negative terminal, but that's the direction of the current flow because current goes from positive to negative. Okay, so that is how I determine my Fleming left hand rule. So please do determine one thing. Fleming left hand rule can only be applicable if the thumb and the pointing finger are 90 degrees, the pointing finger and the middle finger is also 90 degrees, and then the middle finger and the thumb should be 90 degrees. So this is how we determine Fleming left hand rule. So how I open up my Fleming left hand rule is I'll point up the thumb first, all right, then I point out the pointing finger, and then lastly the middle finger comes out. All right, so that is how I take out my Fleming left hand rule. Okay, so again, I'm going to show you guys one more time. To open up the Fleming left hand rule, put the thumb up first, and then the pointing finger coming up, making a gun symbol, and then finally take out your middle finger pointing like this. So that's how we determine the Fleming left hand rule. Okay, try not to exert too much force, or else your left hand will get in pain now. Okay, so we're going to focus on Fleming left hand rule right now first. Okay, how to determine the direction. All right, so we have this picture here. I'm going to screenshot this and bring it to my PowerPoint slide. Okay, so first thing first, before you start taking out your Fleming left hand rule, all right, first determine the positive and negative. So here, the red color sign they use, red color is positive. So current flows from positive. All right, this is the copper rod. All right, it's already fixed at the terminal, so ignoring that. Then we have another copper wire here. So current will flow from the copper rod, passing through the copper wire, coming back down here, and going back to the negative terminal. So this is the direction of the current flow. Okay, so if our eyes is placed over here, okay, if our eyes is placed over here, I'm going to draw this in a smaller version over on this side. So I have my south pole here, I have my north pole here. I'm putting a circle in the middle to determine the direction of my uh, wire. All right, that's my copper wire. So magnetic field will move from north to south. So this is my B. Okay, and then from this view, we see the arrow. The current is actually moving outwards. So I will see a dot because the arrow is here. Okay, the arrow is pointing like this way. So this is the tip of the arrow. So here is actually a dot. Now, okay, so how are we going to determine the direction here? Okay, let me open this wide, big and wide, and hopefully you guys can see this. Let's see. Hopefully you guys can see this. All right. Memang tak boleh. So, okay. So how are we going to determine this? All right. First thing first, normally what I do is I will let my pointing finger shows the direction of my magnetic field. And when I draw at this part, okay, when I draw at this part, I'm going to restart and explaining everything. Okay. So magnetic field point north to south. I'm going to draw it over here. So this is south. This is north. My magnetic field points north to south. Okay, that's pointing upwards. And then my current is coming outwards. So when it comes outwards, from this view, from the front view, we see a dot. So I draw a dot here. Okay, so the current coming out like this, the on my right hand rule, Fleming left hand rule, my pointing finger points upwards. And then you take out the middle finger and let the middle finger pointing towards you. All right, so pointing towards you would be like this. Okay, pointing towards you. All right, and then you take out your thumb. Okay, so when you take out your thumb, by putting your hand in front of the paper or in front of the screen, magnetic field points up, the middle finger is pointing towards you. All right, and then you take out your thumb, you would actually notice that the force is actually pointing towards the left. So I hope you guys did manage to point towards the left. So this is the direction of the force. So what does this means that, okay, what does this means that when the magnetic field goes up, the current comes out, this wire will move towards the left hand side of the picture. All right, so the magnetic force will move towards the left hand side. Okay, let's practice another thing. Please do remember one thing. It would be the best if you can actually draw this out on a piece of paper. In exam, your paper can move. Don't go and make your hand like this lah, and then you will, and then at the end of the day, you will say that teacher, my hand very pain. Eh. Okay, now let's try this diagram. Okay, so for this diagram, let's see, page 13. Okay, I'm gonna show you this. Okay, first determine the direction of positive, negative. This is positive, negative. Then the direction of current. Current flows from positive, go through this rod, and then comes into this rod. So here's the direction of the current coming out, back to the negative. All right, so this is my direction of my current flow, I. Okay, so that's current flow first. Number two, determine the direction of the magnetic field, permanent magnetic field. So my permanent magnetic field is from north towards south. So I'm going to draw my B upwards like this. Okay, so using your Fleming left hand rule, magnetic field first, magnetic field pointing upwards. The middle finger represents the current, I. So over here, you would see that the current is pointing outwards. So move your hand, your Fleming left hand rule, so that your middle finger is actually pointing towards you, and then you would notice that your thumb is pointing towards the left side. So that's the direction of our force. Okay? So that is how then we will say that this copper wire will move towards the left. All right, using the Fleming left hand rule. Then after that, okay, did you guys get it? Are you able to determine that? I hope you can. Boleh kah? Junsian can. The rest? Can, okay. Now, if can you all please try this diagram and tell me whether the copper wire will move towards the left or towards the right? All right. Determine that and see whether will it move towards the left or towards the right. All right, I'm giving you guys some time. Try to identify whether will it move towards the left or move towards the right. This picture. Okay, Edmund says towards the right. What about the rest? Can give you guys 1 more minute before I start explaining it again. Susiang, yes means apa? Alright, I'm gonna start explaining right now. So first thing first, there's power supply. The longer line represents positive. The shorter line represents negative. So current will flow from positive through the rod to the wire and then coming back to the negative direction. So this is the direction of current flow. So right now we are looking from the front view. So when we look at the front, this is the arrow. We will actually look at the cross, the end of the arrow. So at the wire, we will see a cross. All right. We are talking about this wire right now because this is the only wire that can move. All right. So that's the direction of the current flow, I. Magnetic field is actually pointing from north to south. So that's the direction of magnetic field. So here, magnetic field pointing upwards. So because there's power supply, we have to use Fleming left hand rule. So again, number one, use the direction, the pointing finger to show the direction of the magnetic field. So that would be pointing upwards. Okay. And then take out your middle finger and also the thumb. All right. So magnetic field pointing up, but the current right now is pointing inwards. So it goes like this. All right. You should be in your screen. I'm looking at my screen, so my camera is showing this direction right now. So the pointing finger pointing up, and the current is entering the screen. So you'll be seeing that I'm pointing this finger towards the screen right now, but my thumb is pointing towards the right hand side. My thumb is actually pointing towards the right hand side. So good job to Edmund for identifying it. This wire will now move towards the right. Okay, so that is how we determine the direction using the Fleming left hand rule. All right, but how are we going to determine the direction using magnetic field interaction? All right, so we're going to determine that using the magnetic field interaction. Okay, using the same situation just now. First, we have magnetic field, which is pointing from north to south. So if it's pointing from north to south, it will, yeah, I just noticed that I wrote both south. Sorry, yeah. So pointing from north to south will be like this. Try to use a ruler, please. Not try, must use a ruler, please. Okay, so this is the direction of the magnetic field from the permanent cable. Okay, then after that, I'm trying to analyze this one. The current is coming outwards. So I have a wire that is coming outwards, so I see a dot. So the magnetic field for a wire, I draw 3 circles over here. All right. So using your right hand grip rule, all right, for the wire on the right hand side, using your right hand grip rule over here. So you see a dot, which means that it should be pointing, your thumb should be pointing towards you. All right. Your thumb should be pointing towards you. And when you curl your fingers, when the thumb is pointing towards you like this, when you curl your fingers, you see that your fingers is going anti-clockwise. So the magnetic field lines for the current carrying conductor is actually going anti-clockwise. Right? It's going anti-clockwise this way. So what happens for a catapult effect is that we want to add these two together. So when we want to add these two together, the resulting effect, okay, this is south pole, this is north pole, and then we put a wire in the middle here. Okay, now how we want to analyze is we have to analyze one by one. First, we have to analyze over on the left hand side. All right, over on the left hand side, the permanent one is pointing upwards, but over on the left hand side of the wire, it's going downwards. They are going against each other. The permanent one is going up, but the temporary from the wire magnetic field is actually pointing downwards. So they are actually going against each other. When it goes against each other, they will actually move further away one, you know. It will move further away like this. Now, which line will it follow? Will it follow the temporary one or will they follow the permanent one? My answer is permanent is stronger, temporary is weaker. So the magnetic field lines will follow the direction of the north to south. Okay? And then we analyze the one on the right hand side plug. All right, the right hand side over here, right hand side is going up for the permanent one, and then the right hand side for the wire is also going up. So because both is going up, therefore it will follow up lor. So when this happens, you notice that there's an empty spot over here. So this empty spot will cause this current carrying conductor to move over the left hand side. So that is how we see this one moving towards the left. See? Even the catapult effect, it will show that it's actually moving towards the left hand side. Okay? So are you all able to understand the catapult effect? So this catapult effect is the magnetic field due to the interaction from the magnetic field from a current carrying conductor and the magnetic field from a permanent magnet. That is the definition for catapult effect. Okay? I hope you all can understand how to Identify this catapult effect. Any problem regarding catapult effect? Other response? Other response? Okay, now when a current carrying conductor is in a magnetic field of a permanent magnet, the interaction between the two magnetic field produces a force on the conductor. So the direction of the magnetic field, the current and the force is always perpendicular to each other. So this one you have to identify. It is always perpendicular to each other. Now, how a current carrying conductor in a magnetic field experience a force? Okay, this is what I have mentioned, but I'm going to explain a little bit here first. All right. Magnetor magnet, honestly to say, it's a weaker type of magnet. All right. It will produce a uniform parallel magnetic field. Magnetor magnets are permanent magnets. So then a current carrying wire produces a circular magnetic field around itself. So number one is from a permanent magnet. Number two is from a temporary magnet. Temporary magnet means it comes from a current carrying conductor. So one uniform parallel, the other one circular magnetic field. When the two fields interact, it will produce a resultant field known as the catapult field. So upwards, the two fields are in the same direction. Okay, this one is talking about the other thing lah. So what you need to understand is number one, two, and number three. All right, the magnetor magnets are permanent magnets producing a uniform parallel magnetic field. Number two, temporary magnet, which is actually created due to current carrying wire conductor, produces a circular magnetic field. So the interaction between the two fields will create a resultant magnetic field known as catapult field. So over here, all right, so if I were to explain this, okay. Magnetic field is from north to south. Use a ruler so that you can draw straight lines. And then this is a cross, which means the current is entering my, if it's entering the paper, my hands is actually turning clockwise. Yeah, it's not supposed to touch each other. Please be careful when you draw the direction of the arrow. Make sure it's all in the same direction. So you see at the top part, all right, what happens is at the top part, both of it is actually in the same direction. So here it will actually move together following the direction of the north to south. It will curve a little bit lah, okay? And then the bottom part for the permanent magnet is actually moving towards the right, but for the temporary magnet is moving towards the left. So what happens here is the arrow, I'm coming here because here sudah draw ma. All right, the resultant will be like this. The top part, it's moving towards the right and it's quite closely together, so it represents stronger magnetic field. The bottom part, because the wire's magnetic field is pointing towards the right hand side, the left hand side, but the permanent one is moving towards the left. So this is a region of weaker magnetic field. So the magnetic force will force the wire to move from stronger region to a weaker region. That's why the wire will move downwards. All right. So if you use Fleming left hand rule to determine this, magnetic field pointing towards the south. All right. Fleming left hand rule, magnetic field pointing towards the south. The current is pointing into the paper or the screen, then you will see that your thumb is pointing downwards to represent the direction of the force. All right, so that is further clarifying that the magnetic field is the magnetic force is causing the wire to move downwards. Okay, so over here, let's see what else is in your textbook first. Pattern, sudah draw. Fleming left hand rule, done. Factors affecting the magnetic field. So did they show anything here? Okay, this one in a short while I'll come back and explain regarding this. Now, factors that affect the magnetic field, all right, the magnitude. You have to increase the current, all right. Increasing the current, it will create a greater force. You use a stronger permanent magnet, you will also get a greater force. I have one question. I tak pernah dengar metal magnet. The suggestion for the homopolar electromagnet. Metal magnet. I'm still searching regarding this whether to accept the answers or not. I will find out from Google later on and to discuss with the other teachers. But in terms of the characteristic of the magnet, we will normally use a stronger permanent magnet, all right, or a nodium magnet. Okay, nodium is a rare earth magnet which has a very high magnetic field. Okay, so these are a few ways for us to increase the magnitude of the force on the current carrying conductor in a magnetic field. Okay, so right now, let's go back to the textbook. Okay, now, how do we increase? So, first thing first, we can actually increase number one, all right, over here. What they did was they changed the direction of the current. Okay, let's cross check again using our Fleming left hand rules idea whether the direction is correct or not. So here, magnetic field is moving from north to south, B, and then the current is moving at this part of the rod, it is moving outwards. All right, so wire, we see a dot, magnetic field pointing down. So Fleming left hand rule, let's cross check. Magnetic field pointing downwards, and then the current is coming out. So the current should be pointing towards you, and your thumb will point towards the right hand side, so the direction of the force. So that's why this one will move towards the right hand side. Okay, so then what they did was they increased the current flow. When they increase the current flow, this wire move further up. It actually swings higher with a larger force. All right. So that is one method to increase the current flowing in the conductor, in the wire. The second one is they got the wires, the magnet, all right, the poles of the magnets to be closer towards each other. So when it's closer towards each other, it will have stronger magnetic fields, therefore creating a larger magnetic force, and again it will swing higher. So over here, in conclusion for this picture, what they did was, okay, they increased the current. Okay, let me move that. Okay, when they increase the current, okay, there will be larger, right, more magnetic force, hence the wire swings higher. All right, so they increase the current, and then more magnetic force will be produced using the Fleming left hand rule. The wire will swing higher. Over here, they actually brought the distance. All right, they decrease the distance between the wire. Between the magnet. So when they decrease the distance between the magnet, it will create stronger magnetic field. When stronger magnetic field, the same current produced, it will create a larger magnetic force. right? And therefore it will swing higher again. Okay, so that is a few of the methods for us to determine the direction. Okay, I hope you guys can see that. All right, so that is how we increase the current in the magnetic field on the force. Okay, another method is actually to increase the number of magnets. When you increase the number of magnets, that means to above and below it, all right, you will actually increase the magnetic force as well. Okay, so let's see. All right, if this case is actually to let it swing, in this picture, it's actually making it move away. So the distance traveled by the conductor, all right, will show whether the magnetic field is stronger or not. So the larger the force, the further away that this distance of the conductor will actually move further away. Okay, all right. So I hope that would be all right with you guys so far. Are you guys okay so far? Thank you, Sarash. The rest? The rest still in or not? Okay, so okay, good. Thank you for replying. Now, so we are gonna go into motor right now. Okay, now identifying motor and generator. Where is my okay? A motor. Normally, when we talk about motor, we talk about only direct current motor. Okay, we talk about direct current motor to be focused, and then over here when we talk about motor, it means that there is power supply. Having power supply means there is current flowing in the circuit. Okay, so that is actually for motor. Motor, for direct current motor, there is power supply, there is current flowing in the circuit. Now when we talk about generator, generator means to generate electricity. You know, when you go to pasar malam and normally you would hear the under each store you will hear a very very noisy sound. Those are generators, all right. Its main function is actually to generate electricity. So when you generate electricity, you can have direct current generator. You also can have alternating current generator. All right, so for generator wise, we will discuss that in the next lesson. All right, so we are going to focus on motor first, direct current motor. Okay, so what happens here is that we take a single wire, all right, a single piece of copper wire, and then we bend the wire to look like a rectangular coil. Okay, so we have the parts of A, B, C, and D in this situation, and then we take this coil, we connect it to our power supply. Okay, we will either determine the direction of the positive and the negative for the power supply later on. All right, either positive or negative. So the current will flow from positive to AB, BC, CD, and then back to the negative terminal. Depending on the west direction of the positive and negative, please do not go and memorize the positive and negative. Okay, we analyze it from the power supply, whether it is positive or negative. Current will always flow from positive terminal to the negative terminal through the external circuit. So right now, the external circuit is the copper wire. Okay, so over here we will be looking at this. All right, the same rectangular coil just now is connected to a commutator. When you see this shape, all right, this shape of a two metal C like this is commutator. Ayo, why writing so ugly one? All right, this is known as a commutator. Commutator main function is so that the current coming out is always the same direction. All right. So for example, if I consider this as terminal X and this is terminal Y, the current will always enter this side positive and the current will come out here negative for a motor. Commutator mains function is so that the current that is entering or coming out is always the same direction. Okay, so the current carrying coil, there's current carrying, so we know it's going to be using Fleming left hand rule. All right, so it will actually cause the when there's current carrying, which means there is going to be temporary magnetic field, and then it is in the middle of two permanent magnets, so there will be an interaction between the permanent magnetic fields and the temporary magnetic field from the wire. So we know that there's going to be using Fleming left hand rule. Okay, so the rotation is actually due to a pair of forces of equal magnitude but opposite direction acting on the sides of the coil. Which side? Side AB and side CD. Okay, we will not discuss about side BC because magnetic field is moving from north to south, and then the current is actually moving from B to C. They are parallel to each other. When the magnetic field and the current is parallel to each other, there will be no force. It will only have force when the magnetic field and the current is 90 degrees or even a slight angle, there will be a force. But in SBM, we talk about full 90 degrees. Okay, so this pair of force is produced by the interaction from the current carrying conductor, the temporary magnet, and the magnetic field from the permanent magnet, the magnetdoor magnet. Okay, so we're gonna discuss how this thing works. Okay, so this is north-south current entering. Okay, I'm going to use back this image here. And I'm going to screenshot this so that I can actually draw this at my PowerPoint slide. Okay, so I'm going to analyze this. This one should be, let me see whether the picture is the same. Cross in, out. Okay. Give me 1 minute to drink water first. Okay. All right. So right now, I'm going to analyze one by one. Okay, I have my south pole here. I have my north pole here. Okay, so first determine the direction of positive and negative. Positive here, currents entering the positive, going into the red color commutator, entering A, going towards B here. Okay, so if I draw two circles to represent the wire, here from the outside view, if I look from here, I would see that the current is entering from A to B. So on the left side, I would see a cross. Okay. And then after that, the current will flow from B to C, C to D. And then coming up from the blue color line towards the negative terminal of the power supply. So if we were to look at point D, if we place our eyes at point D, we would see the arrow coming out. So we will see a dot here. So this wire is a dot. Okay, so let's get ready. Yeah. So using our Fleming left hand rule, magnetic field is actually pointing from north to south. So this is my B. Okay, I'm gonna analyze the left hand side first. So again, magnetic field, we will start with magnetic field. So magnetic field pointing towards B. All right. So, okay, magnetic field pointing towards B. And then my current is actually pointing into the screen. All right. So what I did right now is my magnetic field is pointing towards the left hand side. And then when I take my current up, I use my right hand to move my thumb in front. And obviously, it would be much more better if you draw the picture and you put it onto the table. Okay? Because it would be much more easier if this question is on the paper. Because the paper is downwards, so your hand won't be that in pain. And remember one thing in SPM exam, please don't stand up to do your Fleming left hand rule and right hand rule. Alright? The examiner will think that you're trying to cheat. So point towards the left, magnetic field towards the left, my current pointing into the paper, my thumb is actually pointing upwards. This is my direction of my force. Okay? So don't hold your hand too long over there, or else you'll have a very sore arm. Alright, then we look at the right hand side. Right hand side, again, magnetic field is pointing towards the left. Now the thumb have to the pointing middle finger needs to point towards you. Okay? And the thumb now points downwards. Fleming left hand rule, the thumb points downwards. So this is F. Okay? So remember, this is the whole entire coil. So when this happened, AB is moving up, CD is moving down. So what happens is this coil, one side being pushed up, the other side being pushed down, this coil will actually rotate clockwise. Alright? It will actually turn clockwise. That's the reason why inside your textbook, the force is going up on the left and then on the right is going downwards. So here we would see the coil axis rotation is going clockwise rotation. All right. So up to here, any question? No, okay, all right. Okay. So I'm gonna base on Sarah's response saying no teacher and the rest not response. Okay, so over here, if you look, this is what we have analyzed. This is slightly different from the picture that we analyzed just now. Why? Because just now the picture, the south is on the left, the north is on the right. Okay, in this picture, the north is on the left, the south is on the right. So on the left hand side, the force is pointing downwards, and on the right hand side, the force is pointing upwards. Okay, so you use your Fleming left hand rule and right hand rule to determine the direction. Now, what I want you guys to focus right now is the commutator. Okay, focus on the commutator right now. At the commutator part, what happens here is that you can see on the left side, it's orange color. Current goes from positive to the orange color commutator, entering A to B. All right. And then C to D coming out from the blue commutator to go to the negative terminal. When it turns already, the blue color will actually flip towards the left hand side. So when it flips towards the left hand side, because it have to follow the direction of the positive and negative of the direct current, current will enter through the blue commutator right now to go into the circuit, and then it goes from D to C, and then C to B, B to A. And then from the orange color commutator, it goes back to the negative direction. So always the commutator, remember the function is always that the direction has to be the same. So forever on the left side, the current will enter. See, on the left side, the current will enter A to B, here D to C. And then on the right side, the current will come out from B to A, C to D, so that it will come out back towards the negative terminal. So that's the main function of the commutator, to make sure that it enters and come out same direction for the current. Okay? Now, so I hope that one is okay with you guys. How are we going to increase? All right. How are we going to increase the commutator? All right. So if we want to make this turn faster, okay, so let's see if there is anything inside the notes. Okay, yes, there is. So how are you going to increase? You increase the current in the coil, All right. So if you increase the current in the coil, you actually increase the magnetic field strength. I know you all cannot see, so I'm going to bring this down. If I cannot see, I'm sure you all cannot see also. The strength of the magnetic field increases. How to increase the strength? To use a stronger magnet. All right. All right. When we're talking about just now that motor, the DC direct current motor. All right. DC direct current motor, you can use a radial magnet. Radial magnets means instead of just a magnet bar, you can actually make a circle magnet. All right, a circle radial magnet. All right, that one we will increase the magnetic field strength also. All right, but another answer, if you don't want to keep repeating to use the word increase magnetic field strength, you can actually use the word increase the magnetic force. Okay, that is also acceptable. The coils with more turns, all right, more number of turns being used, reason explanation so that to cut the magnetic field lines more, all right, or to cut the magnetic flux. All right, so this is a few methods for us to increase the turning effect. Okay, so I guess you all want to copy this first. If you all want, please do go ahead. All right. So let's see what else do I have here that I want. Okay, now this is a few things that I think you can screenshot this. All right, these are some of the functions. All right, that's not mentioned inside the textbook. A commutator reverses the direction of the current in the coil every half rotation so that the coil continues to turn in the same direction for a direct current motor. Okay, carbon brush is here. Carbon brush is to contact the commutator so the current from the battery enters the coil. And the spring's main purpose is to push the brush so that it's always contact with the commutator. So, in another words, to say when the coil turns, there will be a carbon brush and it will always be in contact. All right, so this one will create friction, it will create sparkling. What does sparkling means? You know how lightning happens? Lightning happens when there's too much of negative charges at the cloud, and at the residential areas there's too much of positive charges created from all the electricity that we use. So the currents, the negative charge will actually move from the cloud coming down through the air and towards the earth in order to neutralize itself with the positive charge. So sparkling happens when the negative charge or the electrons is moving from the carbon brush to the commutator. So when it jumps from the carbon brush to the commutator or from the commutator to the carbon brush, you will see a spark over there, and that spark is the same spark that how lightning happens. Okay, so that is the explanation on sparkling lah. Okay, I've explained all this. One more thing that you all can see: area of the coil. Inside the textbook they mention about current, they mention about the number of turns, and we mention about the strength of the magnetic field using a stronger magnet. Another one is area of the coil. If you increase the area of the coil, all right, the magnetic force that is created will be stronger as well. Again, um, the actual explanation is because you need to cut the magnetic field lines. So when the area is bigger, it's easier to cut the lines and to produce that magnetic force. All right. Again, the actual formula is inside pre level, which you all don't need to know at this level yet. All right, so I think that should be it. Okay, this is the question that comes out from the trial question the other day: brushless motor and brushed motor. Now, the difference here is, if you can see, the coils the coil of the copper wires are inside for a brushless motor, there's only two wires coming out. But if you see at the brushless motor, there's no wire coming out on. All right, the one that is inside, it's still the coil, but the magnet is outside, and you have a commutator here. Okay, so there's a carbon brush located at this part. All right, there's a carbon brush located at this part, but there's no carbon brush for the brushless motor. That's why, hence the word brushless. Okay, so the similarity and the differences between a brushless motor and a brush motor: number one, both has magnet and a coil. All right, it uses magnetic force to produce the rotation. All right, motor means it uses electricity to create magnetic field in order to create the magnetic force. It's the magnetic force that produces the rotation. The differences for brushless motor is that the coil is stationary, it's the magnet that rotates. But for a brush motor, the magnet is stationary and the coil is the one that rotates. So brushless motor, there's no carbon brush, therefore there's no friction. When there's no friction, there's no sparkling. And when there's no sparkling, it's actually much more softer. Another differences is that, all right, brushless motor is more efficient. All right, it's more efficient compared to the brush motor. All right, because I did some research regarding this. All right, so the brush motor is less efficient. In terms of efficiency, brushless motor is around 80% to 90% efficient to convert electrical energy to kinetic energy. But for brushed motor, because there is friction, there will be energy loss, there will be the in terms of heat and also in terms of sound. So it is less efficient, roughly around 70 to 80% efficiency only. All right, so that's the difference between brushless motor and brush motor. I think that should be about it. All right. So up to here, do you have any questions that you want to ask me so far? Neodymium magnet is spelled here. Neodymium magnet. Neodymium magnets are normally the small petite punya magnet. All right. Okay, up to here, is there any questions that you want to ask me?